Again, good afternoon or good morning, depending on where you are. It looks like we have a solid number of folks connected here. So we'll get started. My name is Ben Sade. I'm the Associate Product Manager for the Pavement ME product at AASHTOWare. Next slide, please. Just a couple of housekeeping items before we get started. This is the first webinar in a 4-series of webinars for this fiscal year of 2026. Today, your moderator will be myself. Hari was not able to attend this webinar. We will hear from John Donahue from ARA, presenting on the rehabilitation strategies for concrete pavements and AASHTOWare Pavement ME Design. This webinar, along with future webinars, will be recorded and they'll be posted to our YouTube channel, as well as the Pavement ME Design website. Next slide, please. The Pavement ME Design Task Force is led by Ryan Fragapane and myself, along with task force members Hari, Ian, Nusrat, Kumar, Dolce, Jason, Robert, with liaisons from the Canadian TAC and Tom from Federal Highway Administration. Next slide, please. Everyone attending the webinar today will be on mute. We are able to answer some questions as time permits during the end of the webinar. If you navigate to either the bottom of your screen or the top of your screen, if you're on a mobile device, you will find a Q&A session. You can click on that Q&A box and enter in questions. If we're unable to get your questions answered during the webinar, someone will reach out, provided you leave your contact information, and provide you with an answer.
Yeah. Okay.
At this time, I'll hand over the mic to John Donahue, who will lead us through this webinar. Thanks, John.
Okay, thank you, Ben. All right, before we start the webinar itself, I do want to mention the prerequisite for the webinar, which is having some prior experience with using the Pavement ME Design software, whether it's the desktop or the web version for new concrete pavement design. There's a lot of things we will not be discussing in this webinar because the assumption is that you have some familiarity with it, such as the traffic module, the climate module, most of the material input data as well. The webinar will highlight areas where there are some differences as far as the user inputs go. But anyway, it's not that you won't get anything out of this if you don't have that experience, but it would help a lot to kind of use that as the jumping off point for what we're going to talk about. And with that, we'll talk. The learning outcomes out of this is we're going to first list the different rehabilitation options that are available for both jointed plain concrete and continuously reinforced concrete pavement. We'll understand what factors going into considering the selection of the appropriate rehabilitation treatment, which is going to be tied back to the existing condition of your concrete pavement, essentially. And then, as I kind of mentioned already, we will talk about any differences in the material or design property inputs that are there for rehabilitation versus new pavement design. And sprinkled throughout the presentation, I'll bring up jointed reinforced concrete pavements, how those can be handled or maybe not handled with certain of the models. And the reason why it's good to mention this is because there's still a number of states that have a legacy of jointed reinforced concrete pavements, and the performance models were never calibrated specifically for jointed reinforced. It's always been either jointed plain or continuously reinforced concrete pavement. However, when you're rehabilitating, especially if you're covering it, there are some ways that you can incorporate JRCP into the pavement ME design. And the specific topics, we will go over the condition assessment, things that can be looked at for the current condition of a concrete pavement, and gauging the severity level. And then we'll get into basically the 5 different categories of models that are in pavement ME design. Jointed plane restoration, which is only for jointed plane concrete. There's no CRCP restoration option. Bonded concrete overlays on either jointed plane or continuously reinforced. Asphalt overlays on either of the 2 pavement types. Unbonded concrete overlays on jointed plane or continuously reinforced, and asphalt overlay on fractured jointed plane or continuously reinforced. And several of these, 2 or 3 of these, have subtypes that we'll discuss. So there's more possibilities to select for some of these categories. And finally, we'll kind of summarize it with some of the primary takeaways of the webinar. Now, as a reference, the information provided in this webinar can be tied back to certain chapters in the AASHTO Manual of Practice, the AASHTO MEPDG Manual of Practice. Specifically, Chapter 9 covers the pavement evaluation for rehabilitation design, which would be your condition assessment of the pavement. And then Chapter 12.2 covers rehabilitation design with asphalt overlays, and the next one, 12.3, covers rehabilitation design with concrete overlays. Okay, starting with the first item, condition assessment of rigid pavement. The things you can do are doing, one is a condition survey to measure the number of cracked slabs in jointed plane or the number of punch outs per mile for CRCP. You can back calculate information for jointed plane concrete pavement. If you can back calculate the concrete, the elastic modulus, and then use the correction factor to get the static value, which is what you would input in pavement ME design. You could also back calculate the resilient modulus values, obviously, of the lower layers, the unbound layers. Or you can just go straight to calculating what the dynamic K value is. And the K value is what is used for the foundation support engineering property in the analyses. And so you'll have an option, we'll talk a little bit about it, where you can do a conversion from the lower estimated resilient moduli to get K value, or you can input it directly if you wish to. Load transfer efficiency of transverse joints and cracks. That's important because it will be used as a design property in helping to estimate what the amount of reflective cracking that's going to occur through asphalt overlays. Void detection at corners, and this is primarily to figure out, if you have to do repairs, you're going to have to restore the concrete pavement to some extent in order to do some of these rehabilitation treatments. So you're going to have some type of minimum performance level. But with the FWD, does a pretty good job of, there's a method for estimating voids under using the relationship between the load and deflection. And finally, concrete strength testing. You do have to estimate or input flexural strength, and essentially you can backcast that to estimate what the 28-day design strength was initially. There is a table in the manual of practice that kind of helps you gauge the level of, or your serviceability level, if you want to call it that, of the pavement that you're evaluating. It covers jointed plane and CRCP, but it also actually has a few entries for jointed reinforced concrete pavement too. So you can, if you are covering up the JRCP pavement, you can kind of use this criteria to help you determine what some of the design property inputs are going to be. So what are our options we could do? If the jointed plane concrete pavement has minor structural distress levels, that can be a good candidate for restoration using the restoration module. If you have minor structural distress levels, but you may need additional structure, bonded concrete overlay is a possibility. Well, maybe not a strong possibility. We'll kind of get into that when we cover this. And if it has moderate structural distress and may need additional structure, that might be the right kind of the sweet spot for considering an asphalt overlay. If you have moderate to major structural distress levels in either type, at that point, you may have to go to an unbonded concrete overlay. And finally, if you just have major structural distress levels that would cause you to distrust any of the overlay options, then at that point you can look at fracturing the concrete and placing an asphalt overlay on it. So these 5 models are all represented in, or these 5 rehabilitation treatments are all represented in performance models in the Pavement ME Design program. So some guiding principles that pretty much cover all the types of rehabilitation strategies that we have here. So keep these in mind. The fact that the material properties of the concrete or asphalt overlays and existing layers are the same as for new rigid and flexible pavement design. So we're not really changing anything there. The model and the transfer functions are also the same as for new pavement design, except that if you are placing an asphalt overlay on the concrete pavement, then you're also going to include the reflection cracking model as well in the estimate of primarily the total transverse cracking. Okay, so let's get into some of the specific treatments here. JPCP restoration. This is just showing you a screenshot when you initiate the project. So you're going to be selecting for design type. For the drop-down menu, you can select restoration. And for pavement type, there's only one to select, which is jointed plain concrete restoration. As I said, that option isn't there for CRCP. So what kind of pavement would we select for doing restoration? No significant cracking. Obviously, you can address cracking through as much full depth repair as you want to do, but from a cost effectiveness standpoint, it's probably not a wise choice. At that point, you'd be better off doing one of the more heavier duty rehabilitation treatments. No severe faulting typically. I say typically because you could have a situation where the original concrete pavement did not have dowel bars, and so you might have had somewhat significant faulting occurring because of that. However, the subgrade itself is still in pretty stable conditions. So really, if you do dowel bar retrofitting and then you diamond grind the surface, that could still be a good candidate for restoration if you don't think that loss of subgrade support is gonna haunt you in the future. So that's why I say that it's generally severe faulting would be an issue, but you have to evaluate the foundation condition. No significant durability problems. In other words, no concrete cancer, decracking, alkali silica reaction, some of the other nasty things that can happen to concrete. Once it starts, it's going to continue. And really, at that point, if you want to retain the concrete pavement in some manner in the structure, covering it up is probably the best thing you can do because that will slow down or inhibit the infiltration of chlorides and other nasty things that get into it through water or precipitation. And, you can slow down the deterioration in the concrete pavement and get more life out of it. No significant subgrade pumping. I kind of alluded to this with the cracking issue. So if you have pumping going on, you have to do something, either through a combination of retrofitting, undersealing, slab replacement, maybe even undercutting and putting some select fill in areas. But that definitely is not a restoration candidate if that's happening. And as far as JRCPs go, no, you cannot do restoration modeling in pavement ME Design with a joint reinforced concrete pavement because it's not being buried where its properties become less significant. You're still stuck with that as your final product, and the model simply wasn't calibrated for the longer joint spacing and mesh reinforcement. So as far as treatments, what would you do prior to running the design? Full depth repairs. Again, if you want to, from trying to be cost effective, if you run over some theoretical percentage of full depth repairs that are required, at that point, you should be looking at some other rehabilitation strategy. And partial depth repairs. Now, there may be more of these. They're in spot locations generally, and if whoever's doing the partial depth repairs, if they do it according to proper procedure, which is another topic in itself, they should be long-term fixes. So they're a good solution when done right. Dowel bar retrofitting. Especially if you don't have dowel bars at the joints right now, they'd always be strongly encouraged to include those. Cross stitching, this is a lesser known treatment, but it's in the situation where you do have some uncontrolled longitudinal cracks. They might not have opened up yet, but the potential is there in the future. And if it opens up a little bit, you have a little bit of settlement, you could have faulting longitudinally. So cross stitching isn't really meant to solve the loss of load transfer so much as to keep slabs together so they don't walk away. But keeping the crack tight provides you aggregate interlock, so it does help with load transfer as well. And undersealing. Again, you shouldn't have severe, it shouldn't be used to solve severe pumping problems. It'll definitely help, but it's more so when you detect a void through FWD testing, just to try to prevent that from being a problem in the future. And finally, diamond grinding, which is kind of icing on the cake. And this is where you really hit the reset button. You've done all your other restoration treatments, and finally, you grind the surface and you're back at some, hopefully at least the whatever the IRI was at the date of construction, if not better than that. And generally, it should be better than what it was constructed at. As far as the structure, when you do the layer selection, it's the same as a new pavement. It's you're not adding any layers to it or any overlay to it. So it's your concrete pavement. All the design features and properties are the same. The performance criteria is the same as for new jointed plain concrete pavement. Now your IRI that you're setting, the initial IRI, again, take into account the restoration treatments you did to it. So if you do a bunch of patching and you don't grind it, it's probably going to be a little worse ride-wise, unless the contractor did an excellent job of finishing the repairs. But generally, it's kind of hard to do. You're better off, again, grinding the final surface. And then here you would estimate whatever that number is going to be in your initial IRI for performance criteria. Now, the elastic modulus of the existing slab must be compatible with flexural strength. And what that really means is the relationship between modulus and flexural strength should be kind of in lockstep along the maturity curve that you would normally see for both properties. The problem is if you have the flexural strength that is too high in terms of the elastic modulus, then your fatigue cracking could go to almost nothing. The reverse of that is if your modulus is too high with respect to the elastic modulus is too high with respect to the modulus of rupture, then you could have a much higher quantity of cracking that should actually occur. So again, if you're starting with a new pavement, you have your regular 28-day strength estimate. Different input levels are available. Level 3 would be using the inputting compressive strength this is for new pavement, and then 28-day strength at level 2 for modulus rupture, and then finally the 3, 7, 14, 28-day, creating the strength gain curve would be your highest level input. In this case here, you've got an existing pavement, so you have to estimate things, what they were originally. And so you can do a core, break it, get an estimate of compressive strength, and then try backcasting that to what the 28-day strength would have been. And then obviously for the elastic modulus, you could also do back calculation estimate or from FWD and get that number. But it's important to make sure that I guess I should have included a curve here to show you the relationship between flexural strength and modulus, how that if you go above or below that line, you're going to either increase or decrease cracking. And if you are back calculating, I already mentioned measuring or multiplying the dynamic value by 0.8 to convert to static value for elastic modulus of the concrete. And then backcasting that static value to the 28-day elastic modulus. So it's compatible with whatever your estimate of the 28-day flexural strength is. Now, for the lower levels, the unbound levels, unbound layers below the concrete pavement, a couple things you can do here. One is if you are back calculating the elastic moduli of each of the layers and you input those, you can let the program estimate the dynamic modulus of subgrade reaction. If you don't, you could also input it directly. So if you input it directly, if you've estimated or calculated that from your FWD data, you can input that, and then that overrides whatever resilient modulus data was there for the unbound layers below that. So ultimately, the actual engineering property input used in the analysis is going to be the modulus of subgrade reaction, or your K value. Now, as far as the existing fatigue damage, we're using the difference and the slabs replaced after restoration. So in this case here, if we have 15% cracked before, 10% cracked after, the difference is going to be 5%. And there's a relationship between fatigue cracking and the damage. And so in this case here, if we're going to says AC, that's not correct. This is for concrete. But anyway, there's the relationship between fatigue cracking, measured fatigue cracking, and I'm sorry. Okay, sorry, this is wrong. Okay, yeah, I apologize. Wrong graph here. This should be transverse. It should be fatigue cracking in the transverse slab. So just imagine that the curve is going to look somewhat similar, but there's a relation. You're relating the number of cracked slabs to the damage index. And so that's what determining the difference between before and after slabs does. And then I mentioned this already, the fact that if you want to let the Pavement ME Design program calculate the unbound layer modulus subgrade reaction from the resilient modulus values, just leave the box unchecked. You check it if you're if you're going to input it yourself, though. Okay, bonded concrete overlays on jointed plane and CRCP. So here again, this is the opening screenshot. In this case here, pavement design type, you're going to select first overlay rehabilitation, pavement type, bonded PCC over JPCP, or there's also bonded PCC over CRCP. Two types. And so what's going on? So with the bonded concrete overlay, you're essentially creating a monolithic structure between the old and the new concrete. It is the least common pavement treatment, and probably for good reason. These models were all globally calibrated primarily with long-term pavement performance information, and that's data that was derived from the experiments going back over 30 years ago that were set up to have a statistically representative number of sections to look at. In the case of bonded concrete overlays or bonded concrete overlays on concrete, there were not enough sections. Nationally, there were only 4 sites. So instead of being a full-fledged experiment, it was the SPS7 experiment. It was basically reduced to kind of a case study situation. So from the beginning, there really weren't a lot of pavements to use for the calibration. Now, why don't people do this? Because there's a lot of difficulty in trying to get it right. When you do, always have to, as with any overlay strategy, which involves a grade increase or a profile increase, you do have to consider clearances at bridges, transitions to bridge approaches, and then just any grade changes in general as it affects guardrail and slopes and other roadway features. So always have that in mind. So this is very high risk, high reward because there's two things for jointed plain concrete pavement. You have to really prepare the surface well to ensure bond. And it's kind of I know from personal experience being involved in scoping these projects, or a couple of these projects, and being there in the field as they were being constructed, it takes a lot of quality control to really make sure that the amount of sandblasting and shot blasting is appropriate. It helps to do pull-off tests on the surface just to make sure that it's that good bond is available. And really, this is kind of done all the time on bridge decks. But bridge decks are a smaller area that you can focus attention on more strongly. In the case of a pavement, it's a much broader surface area, and it's kind of difficult to maintain the level of quality control that you need to make sure the surface is prepped. The second issue is joints. Not for CRCP. CRCP, because the cracks are tight, you can, I guess, just basically pave right over it. I don't have personal experience with concrete overlays on CRCP, but that's the theory is that you really shouldn't have uncontrolled cracking resulting from the CRCP cracks. However, jointed plain concrete is a different story. You have more movement at the joints. And if you have working cracks in the joints as well, those also can affect the overlay or cause debonding. So what you have to do is saw all the way through the overlay and match the transverse joints and cracks as best as possible. Longitudinal cracks too, you also try to match those. You don't have to saw all the way through, but the point being here is that these two items, preparing the bond and trying to match saw joints, is not easy. And so anyway, it just the overlay strategy is in Pavement ME Design. It's something you can do, and so we're discussing it. But there's a reason why, if it's done right, it's fantastic, because you didn't have to add too much structure, and you basically have a new monolithic pavement that has more structural capacity, but setting it up though is the trick. And since bonded concrete overlays were not calibrated for jointed reinforced concrete pavement, you don't want to do a JRCP and the bonded concrete overlay model. And the structure looks similar to, well, it's just placing concrete over. Now, one issue here, which quite honestly, I wasn't fully aware of till I was going through this, was that there's a minimum overlay thickness, which in my opinion is a little excessive, but this is what the minimum thickness has to be, is 6 inches, if you're doing the bonded concrete overlay in Pavement ME Design. So. And as far as the fatigue damage, you're using the same fatigue damage calculations as restoration. For CRCP, you're not doing a difference between before and after slabs. You're basically assessing it from the number of punch outs, and this is actually the correct graph. So I apologize about the previous one, but this is the punch outs per mile versus damage index. So in this particular example, we have 3%, or I'm sorry, three punch outs per mile, and you relate that to the damage index, and that's going to be your starting point. So in the analysis, your existing concrete is at that fatigue level, and then the fatigue damage that accumulates after that point is basically going to be assessed from that starting point. And kind of the same thing, your common thread you're going to see is, if you're doing back calculated unbound layers, multiply those by the C values to get the laboratory resilient modulus, or if you just want to input, and you can use that then to calculate the modulus subgrade reaction. But again, you do have the choice of checking that box for that table or for that entry in design properties, and inputting your own K value. Okay, next topic is going to be asphalt overlays on jointed plain concrete and CRCP. Initial screenshot again, you're selecting first overlay rehabilitation, and pavement type is going to be either AC over JPCP or AC over CRCP. So again, what kind of pavement are we going to be placing asphalt overlays on? It should be in halfway decent shape. Asphalt will cover some issues, but not all. And if you do have, some severely cracked slabs, then you should do full depth repairs. Partial depth repairs aren't as essential. You could obviously fill those with asphalt or patch them with asphalt as you're going over typically, but if you want to restore the surface to its original condition as much as possible before doing an overlay, you can do a partial depth repair with some type of cementitious material. Dowel bar retrofitting, definitely if you do have low transfer problems, those would reflect it either quickly or maybe delayed to some extent, depending on the thickness of the asphalt overlay. But it's still going to be a problem, and you really want to make sure that you have good load transfer across joints and cracks. Under sealing, kind of for the same reason. You want to prevent movement of the slabs because those can reflect through fairly quickly. And the overlay itself, again, is either going to provide, you can always correct surface conditions. So you can restore ride, you can cover up low to moderate faulting, and depending on the thickness of the overlay, you may actually be adding real structure to the pavement, which would now be a composite pavement structure. As always, take clearances, transitions to bridges or structures, and grade changes into account. So thin overlays, you are restoring ride, but you're not adding significant structure, and you will get reflective cracking through probably within the first couple of years at joints. And if you do have working cracks, by working cracks I mean a crack that's opened up enough to where the aggregate interlock isn't working anymore. It's not providing you load transfer, and you really don't have any. If it's plain concrete, you're not going to have any load transfer steel across there either. So sometimes your working cracks are going to be worse than your joints. So just something to keep in account. And again, you can address this through doing a full depth repair, so you're not going to have these cracks as an issue. For the thicker asphalt overlays, again, you're still restoring ride, and you are adding structural capacity, and you are slowing down the rate of reflective cracking. But from my experience, no matter how thick the overlay is, it could take a while, but eventually you are going to see some reflection through there at some point. But there's ways of mitigating it through the asphalt mix selection, especially if you're doing some specialty mixes, high mod with polymers or SMAs. Again, from experience, I've noticed that SMAs don't necessarily prevent a reflective crack from showing through, but it does lessen the severity of the crack. So it is some of these surface mixes are effective at mitigating either the amount or the severity of reflective cracks. And one solution that has worked pretty well is anticipating the crack by sawing and sealing over the joints, cracks or joints in jointed plain concrete. And that way you're going to force the reflective crack to basically meet where you saw it and seal it. So you're going to have a nice, neat sealed joint in the asphalt across the pavement, and you're not going to have a ragged joint to have to deal with. So depending on thickness, and the other thing too is the overlays, the thicker ones actually can reduce the temperature gradients through the jointed plain concrete slabs, and thereby you're reducing really the curling stresses that occur, which contribute to increased transverse fatigue cracking. So the thicker asphalt overlays do help mitigate transverse cracking. And again, too, you can also reduce faulting as well, because you're not going to have a severe temperature gradient that could cause the joints to open up more. And then reducing the temperature gradients through continuously reinforced concrete slabs could also help prevent them opening up too much, and so you can actually reduce punch outs too with overlays. Now, in this case here, as far as doing a reinforced concrete pavement, models weren't calibrated for them, but you can really just input them as a jointed plain pavement with longer joint spacing, and if you have working cracks. So let's say common jointed reinforced pavement length in decades past was roughly 60 feet or a little over 60 feet. So if you go out and do an assessment of a JRCP and you see a consistent mid-panel cracks at roughly 30 feet, you could actually model this as a JPCP with 30-foot joint spacing. Is that completely correct? No, it's not. You may have a little bias or a standard error increase by using a jointed reinforced concrete pavement in place of jointed plane. I don't think it's going to be much though, so I think I would feel pretty comfortable doing this. So the actual performance models, and this is the longest list you'll see for any of the rehabilitation treatments. So for AC over JPCP, you have all the you have initial terminal IRI, obviously. You have fatigue cracks. So you're going to continue having fatigue cracking in the concrete pavement, in the lower concrete pavement. You're not going to be, faulting's not going to be an issue. You're not predicting faulting when it's covered with asphalt. And then you have your asphalt overlay models. You have top-down cracking, bottom-up cracking. Those are both fatigue related. Being on concrete, those would be very minimal to negligible. So generally, fatigue cracking in asphalt on a concrete pavement is not going to be a controlling factor. Asphalt transverse cracking, so this is primarily going to be, you do have thermal cracking in the wearing surface mix. You do have rut depth, and then you're going to have total transverse cracking when you combine it with the reflective cracks from the jointed plane concrete below. And then similarly for CRCP, all the same asphalt models, and your CRCP punch outs will also continue as well. So there is a continuance of the fatigue damage predictions for both jointed plane and continuously reinforced concrete pavements. And just to look at the actual cracking mechanisms or reflection cracking mechanisms for an asphalt overlay on whether it's either jointed plane or CRCP, is you have a combination of shear, thermal, and bending. So shear and bending are load related. Thermal is contraction or expansion occurring from temperature changes. And the structure diagrams for jointed plane and CRCP with asphalt overlays. These are the screenshots for both. Okay, for design properties, two things. So you are inputting, as with in the case of restoration, you're inputting the slabs that are distressed or replaced. Slabs that are distressed before restoration, and then the percentage that are replaced or repaired after. And then the difference of that, again, is going to be used in the relationship between fatigue cracking and the damage index. And the damage index is what's used in the performance model. The transverse load transfer efficiency, this is also going to be required because, again, we are interested in modeling the reflective cracking through the asphalt overlay. So we need that initial LTE. And then on the CRCP side, again, you're doing the number of punch outs to determine the initial fatigue damage, again, using that curve, that relationship between punch outs and fatigue damage. And then also looking at the initial crack spacing, because this is going to be used in the punch out model as well. Next category is unbonded concrete overlay on either jointed plane or continuously reinforced concrete pavement. The initial screenshot, in this case here, there's going to be the design type is going to be first overlay, rehabilitation. For pavement type, there's going to be 4 options here. And going through them, you can have jointed plane overlay on jointed plane pavement. You can have jointed plane overlay on continuously reinforced pavement. You can have continuously reinforced overlay on jointed plane and CRCP over CRCP. And in each of these cases here, and we'll talk a little bit about this, you can see you're going to have an inner layer, which is going to serve as your debonding medium to prevent bond between the old and new concrete. And the performance criteria for unbonded jointed plane or continuously reinforced overlays are going to be the same as their respective new jointed plane or CRCP models, as you can see here for both. Okay, so let's talk a little bit about these overlays. For these, you can place them on severely distressed jointed plane or continuously reinforced concrete pavement. I'd say the caveat to that is if you have a serious pumping problem, that may be really testing the limits of the concrete overlays. And I still think it's prudent to either undercut, replace them, or underseal. Maybe sometimes even have to jack the slabs a little bit to restore the original profile before placing the overlay. But it's not a good idea to, if there's an occasional spot, you can live with that. But to have continuous pumping problems, those should really be addressed first, regardless of what strategy you're doing with them. So reflective cracking is not an issue with unbonded concrete overlays because you're more or less designing this as a new pavement on top of a pretty stiff foundation. So you're not anticipating getting reflection cracking. I mean, I've really seen it. I've been around a lot of unbonded concrete overlays in my previous career, and generally that isn't one of the things that afflicted them. And as I said too, you're basically designing a unbonded jointed plane overlay and a continuously reinforced overlay, pretty much the same as you would a new jointed plane or CRCP pavement. In this case here, it's pretty safe to run the model if your base concrete pavement is going to be jointed reinforced, because all you have to do is, we'll see in the next slide, I think it's the next slide or second slide, is you just have to have apply an engineering property for the foundation support. And, your crack spacing, joint spacing is really irrelevant. So an unbonded concrete overlay is probably about the safest strategy to incorporate an old jointed reinforced concrete pavement. Yeah, so all you're doing is just having to estimate whatever the K value is. So, if it's jointed plane, CRCP, or even jointed reinforced concrete, it's just, again, it's just a simple foundation. Now, the inner layer, as I mentioned, is, its main purpose is to prevent bonding between old and new concrete. It can somewhat dissipate vertical strains. For a thick overlay, that's not really that important. If it was a thinner, say a bonded concrete overlay or something like that, then that may, if your overlay thickness is only 3 or 4 inches, it may be something to consider. So, but it's really just a side benefit. The primary purpose of the inner layer is just to make sure that the concrete's not sticking together. Now, right now, the Pavement ME Design program can only model asphalt inner layers, and that's generally because when the models were developed, the concept of using geotextile inner layers, which is very common nowadays, didn't exist. So I wouldn't tell somebody that you couldn't model in the Pavement ME Design program. If you're using a geotextile interlayer, I would simply say just use a 1-inch asphalt layer to represent your geotextile. Is that totally correct? No, that's not. But it's a good workaround method until we do devise a better way of modeling geotextile in the program. And I keep pounding on this, but again, always keep in mind. I always say that pavement designers should put themselves in the feet of, or in the shoes of the roadway designer, the general designer for a project, because that person has to take everything into account. If you're providing the pavement design, that's good. But sometimes it may not quite fit in the constraints that exist within a project corridor, especially if you have a lot of overpasses, if you have a lot of bridges you're crossing. Sometimes the amount of transitioning you would have to do makes it so difficult as to almost force you to look at another option, maybe even reconstruction. So that should be taken into account, and also look at it as what's it doing to the adjacent features too. So a lot of times guardrail does have to be replaced, especially as you're updating it to meet current MASH standards. But if it's already been replaced recently, you don't want to have to reset that. And so that's something to take into account. What are you inconveniencing with your overlay design? Outside of the the bubble of just focusing on the pavement itself, what else is going around you? So always encourage people to look at the big picture. Okay, and our last category we're going to be looking at is an asphalt overlay on fractured jointed plane or continuously reinforced concrete. And we always start with the opening screenshot here. So you select first overlay rehabilitation and select, and now this is the case of, and we'll get into this. So if you're doing essentially a break and seat treatment, you do select first overlay rehabilitation and AC over JPCP. However, if you're planning on rubbleizing the concrete, then use a different design type. You select recycling, and then there's a pavement type for AC over rubbleized PCC. So we'll talk about each of these possibilities. So again, fracturing can either be break and seat, and break and seat. Sometimes I think break and seat and crack and seat are kind of used interchangeably. There is supposed to be some nuance in difference between the two. Break and seat is more geared towards jointed plane pavement, where you don't have any continuous reinforcement. Crack and seat is, I guess, better suited for jointed reinforced concrete pavement, where you're trying to sever the mesh reinforcement and make sure that you have separation at all of your cracks. But here, assuming primarily that we're dealing with rehabilitating jointed plane concrete pavement, we'll just, from here on, we'll just call it the break and seat method. And then rubbleization. So for break and seat, it's kind of like the equipment itself is kind of like a guillotine, and so you're dropping this hammer or guillotine across the entire pavement width, roughly and it could vary anywhere from 1 to 3 feet, but I guess on average, these cracks are going to be about 2 feet apart from each other. And I know there has been an issue too sometimes where the drop hammer force isn't high enough. So sometimes you may see like a chalk line across there, but the pavement isn't actually cracked. So you want to make sure that you are getting a positive fracture throughout the whole slab. A rubbleization, there's 2 primary pieces of equipment nationally that are used to do this. There's the multi-head breaker and there's the resonant head breaker. So multi-head breaker can do the entire pavement in one pass. It's a pretty violent sequence of drop hammers. Just in some, well, it appears to be almost kind of a random, sure it's not random, but it almost looks like a random drop phase across there. The equipment goes pretty slowly, about 2 miles per hour, I'm pretty sure is what I recall. And then the resonant breaker actually kind of like directs all this energy to this shoe that's either 8 or 10 inches across there, I think. And it goes faster, maybe 15 miles an hour or so, but you can only do like the 8 to 10 inch swath at a time longitudinally. Now, there's states have their druthers about these. Some will specify one piece of equipment over the other. My thought on this is that you should really let your specifications control things. And if it's end result or performance specification, the final product should be the basis of what you accept. And, you shouldn't have to worry as much about the type of equipment that's being used on it. But, just for information purposes, this is generally what's available to do that work. And a rubblized concrete layer is going to be like a very, very stiff granular base. I think of it as kind of a huge jigsaw puzzle where the pieces have been loosened but not really separated. So typical resilient modulus values are going to vary between 50 to 100,000 KSI. And the particle size, generally you have the smaller piece because the energy dissipates as it goes through the slab. So it's going to fracture the upper half of the slab into smaller pieces, usually 3 to 4 inches, something like that. Whereas when you get to the bottom of the slab, it could be more like 9 to 12 inches across. So it does get coarser as you get to the bottom of the slab. Now, as far as how do you enter that in Pavement ME Design, currently we don't have realistic gradation selections for rubblized pavement. So I just use generally some default value for a crushed stone base. Again, technically, is that really what it is? No, but it's a good enough workaround. Yeah. So 2 different strategies here for doing break and seat. Then again, you select first overlay, rehabilitation, and AC over JPCP fractured. And if you're rubblizing, then select recycling. And the subtype is going to be AC over rubblized PCC. Okay, and for the break and seat method, we do need to input whatever the reduced modulus is going to be of the fractured slabs, and then also input the transverse cracking and the LTE, which is going to obviously impact the reflection cracking. Now, for rubblized concrete, in this case here, for the resilient modulus, you want to make sure you select the annual representative values. And that's primarily because a rubblized concrete pavement should be pretty insensitive to changes in moisture. So you don't have to worry about seasonal changes to the resilient modulus. Okay, summary, takeaways. Pavement condition determines the appropriate rehabilitation treatment. And as I hammered home several times, consider how the profile increase affects other roadway features. Material design inputs are essentially the same for rehab as for new design. Design property inputs should account for any planned restoration treatments. In other words, the number of cracked slabs is going to determine what your initial fatigue is going to be. And obviously, the degree of load transfer efficiency is going to influence reflective cracks. And then the overlay distresses for jointed plane and continuously reinforced concrete are the same as the new design distresses. And I went over the cases where you could substitute jointed reinforced concrete pavement for jointed plain concrete. So some treatments you can do it, usually with caution, and there's a couple you really can't. And to make sure that oh shoot, I forgot that. So I said you use the recycling and the rubblized layer option, which you're labeling it correctly by doing that. You could technically also do the rubblization in a new flexible design. I'll change this slide, update that. But you could do it the same way by selecting an unbound granular layer in a new flexible design and just assign it, the resilient modulus that you would to a regular rubblized concrete layer. And also as a workaround, if you are using geotextile interlayers for unbonded overlays, then just select a 1-inch asphalt interlayer in place of it. And that is basically it. So Ben, you want to handle the poll questions?
Let's see. There's some open questions here. Let's see if we can get a couple of answers. Jay is asking, as I recall, there is a higher resilient modulus when you have PCCP thickness greater than 14 inches. I think there was a study done on resilient modulus and rubblized air-filled pavements.
That could be because I think for the thicker pavements, your fractured pieces are going to be bigger generally, so that would kind of make sense.
Okay, we got a question from Imran. While modeling rubberized layer and using granular base, which type of unbound granular base is recommended?
Say that again, using ground tire rubber is aggregate?
When modeling rubberized layer and using granular base, which type of unbound granular base is recommended?
Oh, okay. Yeah, it's since you're basically not going to let the resilient modulus fluctuate, use a crushed stone or crushed gravel. Again, because you can't enter the actual gradation. The maximum, was it 3 inches or something, is basically the maximum particle size in the pavement ME design. So, here we're dealing with fractured particles that are up to 12 inches or greater across. We do tentatively, we're planning on putting in more realistic gradation properties for rubblized layers, but right now use that. But it doesn't really matter a lot because you are fixing the resilient modulus. So you have one number annually, and you're not letting the EICM vary the modulus seasonally with changes in moisture profile. So in other words, it's not affected by moisture. It's relatively insensitive to it. So that kind of makes it less important how you're modeling the gradation. But we could do better. It's it would be more appropriate to have representative sieve sizes for an actual rubblized layer. But again, as a workaround, just I would just pick crushed stone, I guess.
Great, thanks, John. We had one question get asked a couple of times. It looks like there's an answer, so I'm just going to read off the answer here. So it was asked in a JPCP restoration. Transverse joint load transfer shows at 50% default, and there are no options to change that value. Why is that? And shouldn't the designer have the flexibility? Looks like the answer right now is that transverse joint load transfer is not an input for restoration. Kind of a follow-up question. Are you asking about longitudinal lane shoulder joint? A checkbox is available to change that specific input. So if the person who asked that question, we kind of asked a follow-up question there. Let's see if there's any additions to that one. Not seeing one. If you'd like a more detailed answer about that question, feel free to send an email to the email address that's on the screen right now. We'd be happy to get you a full answer. Because how the Q&A box is structured, it's hard to do a back and forth. So with that, if you'd like to send us an email, pavementmedesign@aara.com, someone will get back to you shortly with a more detailed answer. I am not seeing more questions coming in, and we've answered quite a few questions here. Really good questions. Thanks for sticking around. Again, apologies for the short disruption, and we'll be in contact soon with the recording and presentation for this webinar. And you can expect an invite to the next webinar to come out within the next few weeks. Thank you so much for your time, and have a good rest of your week.